Now that we have determined the static parts of the cell model, the coulombic efficiency, the capacity, the open circuit voltage curves, we are interested in being able to find the parameters that will give us the dynamic parts of the model. So we need the resistances, the time constants, we need the hysteresis values, and so forth. In order to compute these values, we again need to perform some cell tests to collect data. And because our model form, this equivalent circuit model, is not able to exactly capture all of the dynamics of this cell, it's really an approximation. I would like this approximation to work best on the type of dynamic current profile I would expect in whatever application it is that I am designing for. So if I am designing a battery management system or a model for a battery management system of a vehicle, I would like to collect this data by using a profile of current and voltage versus time that is representative of how that vehicle will actually work. If I am building a model to be used for a cell phone, then I need to have a profile of current versus time and voltage versus time for a cell phone battery that is indicative of how that battery would operate in its application. The closer my lab test is to the reality, the better my model will fit the reality because I am fitting the model to the lab test data. That's just the idea. Here I show you a figure that is a plot of current versus time of something called a UDDS profile. And this is used in testing vehicles or battery systems for vehicles. UDDS stands for Urban Dynamometer Drive Schedule. It really is a table of speed versus time of the vehicle that's used by the EPA to measure the fuel efficiency of the vehicle, of standard gasoline-powered vehicles in a city environment. But we have adopted that profile of speed versus time and converted it with some assumptions into a profile of current versus time for a battery system. And this here is a scaled value of current versus time, so it's scaled by the C rate. So the maximum current is about 1 C, and the minimum current about minus 0.8 C, plotted versus time in this figure. And that was the basic profile that was used in the testing that I will describe, but there's a lot more details that I need to talk about. But keep this in mind that this is the dynamic part of the test, but there are some other parts as well. This dynamic part is repeated over the entire state of charge and temperature range of this cell that we are interested in modeling. If I want to model an area of performance, I need data from that area of performance, or else I am extrapolating, and that's not a very reliable thing to do. So as before, we have different test scripts, and these are done at the different temperatures in order to calibrate our results. The first test script begins with a fully charged cell, so that's the assumption. I start at 100% state of charge. And then in step 1, I soak my cell under test at the test temperature for at least 2 hours to give me a uniform temperature. Now you'll notice if you scroll up the page a little bit that my profile of current versus time has some charge pulses and some discharge pulses, and I don't want to overcharge my battery cell by charging when I'm at a very high SOC. And so step 2 discharges the cell a little bit at a constant current, just enough to deplete roughly 10%. This is not a magic number, but I depleted 10% of the capacity to help ensure that we avoid overvoltage conditions during these charging pulses that are part of the profile. And then we execute these dynamic profiles that I plotted there repeatedly over the SOC range of interest perhaps from 90% down to 10% SOC. Again, we don't want to over discharge either, so we want to stay away from the very, very low state of charge points and the very, very high state of charge points. And most applications will not use the entire SOC range of the rechargeable battery because of wanting to avoid aging. And so a model between 90 and 10% is pretty good. If you need to have a model at the higher SOC and lower SOC ranges, you might consider having a scaled version of this profile in those areas that is a little bit smaller, that again tries to avoid over voltage and under voltage, but still gives you some data in the SOC range that you want to model. Okay, so at the end of step 3, I am roughly at 10% SOC, but I don't know exactly where I am because I know the nominal capacity of the cell, and I even know the total capacity, I suppose, from the testing we did before, but there may be some, maybe the tester did not follow my profile of current versus time accurately, or precisely, probably pretty well, but I want to at least calibrate my results at 25 degrees at the very end. So step 4 says I soak the cell at 25 degrees for at least 2 hours to ensure uniform temperature, and then I bring this cell to Vmin by either discharging or charging until I get there, and that means that at the end of step 5 I know that I'm at 0% SOC. So I'm around 10% there, but I don't know exactly how close. But at the end of step 5 I know I'm at 0%. I make a comment here, this is going to be shown in the figure at the bottom of this page, that we can also optionally do something a little bit unusual at the end of this charge or discharge to Vmin, and that is to use what I call a dither profile. Dither is a name from some control system literature, which has to do with almost a noise signal, but you'll see it's not a noise signal. But a dither to try to eliminate hysteresis and to really get this to 0% SOC. This idea of dither is inspired from magnetic hysteresis, and if you were around and a teenager in the 80s or before, you remember that we listened to music on cassette tapes, and there were magnetic media that carried a magnetic field on it that was the recording. And if I wanted to erase a cassette tape, I would get a big electromagnet to do that. And ideally, this electromagnet is something that would vary frequency. And so the really good ones you would plug into the wall and they would vary the frequency of the oscillation of the AC that was trying to erase this electromagnetism. And so we have a magnetic hysteresis curve. It looks a little bit like the hysteresis curve that we saw. And the goal was to charge and discharge, if you will, this hysteresis element repeatedly over and over and over again, faster and faster and faster, to try to get the hysteresis field to collapse. And that's the goal of this dither here, is that I am subjecting this cell to a profile of a very, very small current, but of increasing frequency that's trying to get this hysteresis to collapse. And I've found this to be really effective in practice by using this dither step, and you'll see it in the results at the bottom of the page. It's optional, but I find it helpful. So at the end of step 5, I am at 0% SOC, and in order to prepare for the next step and also to calibrate the capacity of the cell and the efficiency of the cell, we charge the cell using a constant current. I use a 1C rate until we get to Vmax, and then maintain constant voltage at Vmax until current drops below C over 30. You can also put in whatever the manufacturer recommended charge profile is to get to 100% SOC. And again, you can optionally use a dither profile at the end of step 6 in order to really ensure that you are at 100% SOC and the hysteresis is zeroed out to the maximum extent possible. In all of these steps, we record voltage and current and ampere hours charged and discharge as a function of time. Here are some data. The top left plot shows voltage versus time. And here you can see I started out at some voltage. It actually rested for a period, like we said, and then we discharged 10%. So that initial discharge event was to bring the state of charge of the cell to about 90%. And then I rested after that. And then each one of these things, these squiggly parts of the curve, correspond to one UDDS test. And so I've done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, about 19 of them. That 19th one aborted early because it hit an undervoltage condition. So you can see that these are about, in my case, I scaled them to be about a 4% discharge per cycle. You do 19 of those, it's almost, it's about 80% discharge. So from about 90% down to 10% is roughly the SOC range that was exercised of this cell. And you can zoom in, this is the zoom here on one of these cycles between 3:10 minutes and 3:35, so that one, I guess, is zoomed in over here so you can see some of the details of voltage versus time as the cell responds to that profile of current versus time that you saw on the previous page. All of that is something we are trying to model as accurately as possible with our parameters of our equivalent circuit model. So that's test script 1. Test script 2 says at the end of this I am not at 0%, I'm at roughly 10%, and so I rest at my 25-degree temperature and I discharge down to Vmin, and in this case these are the dither cycles I did. I did 1, 2, 3, 4, 5, 6 dither cycles, each one being, I think, a 30-minute long sinusoidal chirp kind of profile. It starts at a low frequency and gets higher frequency over the 30 minutes to try to eliminate the remaining SOC that is caught up in hysteresis. And at the end of this, the voltage, actually, I didn't plot it here, but actually you can see from test script 3 that the voltage at the beginning of test script 3 is right around 3 volts, that there was really very little voltage recovery here, and you get that voltage recovery if the SOC is really not 0%, if it's really some dynamic effect that is still taking place. Anyway, test script 3, I've got the charge section up to about there, constant current, constant voltage charge, and then I have some dither steps as well. This is the data. That's how I collect the data, and here is a picture showing the data. Now, how do I process the data to get a model? We're going to use it to identify all of the cell parameters except for the OCB relationship, which we've already described. So I can again compute Coulombic efficiency and capacity exactly the same way as I did before. That result corresponded to C over 30 discharges and charges, and this one corresponds to a higher current rate charge and discharge. And we find that the total capacity doesn't change, but the Coulombic efficiency does. So with a higher rate charge and discharge, the Coulombic efficiency tends to be worse. And so if I have scaled the dynamic test to reflect what I would expect in the application, then this Coulombic efficiency that we get here is probably a better value to use in your model than the one we got in the previous steps. But I needed to still compute it in the previous steps to get open circuit voltage curves correctly. Once I have those, I use a technique called subspace system identification to find the resistor capacitor time constants. Now, this is something that I would really love to be able to develop for you. I do develop it in a course that we teach here, ECE5710, which is called System Identification. Unfortunately, it takes half of that course to develop this method. It takes 8 weeks of lectures to develop this subspace system ID methodology. It doesn't take you any time at all to implement it. In fact, it's part of the toolbox that comes with the textbook and also the course notes. You'll see that. So it doesn't take any time for you to use it, but to understand exactly how it works, it's really quite a complicated algebraic methodology, but it's really, really powerful to find all these RC time constants very quickly and very well. So I regret that I can't tell you more than that here, but you're welcome to enroll in the system identification course if that's of interest to you. So magically, I find the resistor capacitor time constants for however many resistor capacitor pairs I have in the model. Then I do something interesting. I guess a value for the hysteresis rate constant gamma. Now we're not going to keep this guess. This is an initial guess. We're actually going to optimize this guess, but this is a starting value. And maybe this is something that you know from a previous cell that's similar, or maybe it's a complete guess. It really doesn't matter that much. But once I have this guess of gamma, I can compute all of the hysteresis states as a function of time. I can compute all the states of charge as a function of time, all of the signed currents, all of the currents through all of the resistors, and in fact all of the open circuit voltages as a function of state of charge. All of those things I can compute given eta, q, the RC pairs, and gamma. That leaves the following unexplained part of the measured cell voltage. Measured cell voltage is V. I subtract from V the open circuit voltage as a function of state of charge. I can compute state of charge because I know Coulombic efficiency, and I know capacity, and I know current. So I can just use the model to find that. And then V tilde is any difference between the measured voltage and the OCV, which is the dynamic part of the voltage. And from our model, this is how we have described that. We've said, oh, well, it's the constant m times h, but I know h. H is here. It's m times h. And it's m0 times s, but I know s. And it's the sum of the RC resistances, times IR, the currents through the resistances, but I know the currents through the resistances. Say, wait a minute, didn't we find the R's already, the RJ's? No, I found the time constants. So I found RJ times CJ. I know that product, but I don't know what is R and what is C independently, it turns out. So I need to find that still. And then lastly, I know the input current, but I don't know R0. So the values I still need to find are M, M0, all of the RJs, and R0. I can arrange this V tilde into a matrix vector form where every row of this equation corresponds to one voltage measurement. I compute this, right? This is measured. This is computed because I know state of charge and temperature. So V tilde, this is known at every point in time in my test. That's known. So I put all of those known things together into a vector y. Then the V tilde we said was m times h, so h times m plus m0 times s, then minus IR times the R's, there's minus IR's times the R's, and then minus R0 times I gives you that. So this expression has everything in it that we have seen. I know everything in this matrix, the H, the S, the I, the IRs. I know that. I don't know X. X has 4 components at least, depending on how many RC pairs. So it's 3 plus the number of RC pairs in it. and that's it. The A matrix has as many rows in it as data points in my test, and it has the same number of columns as X has rows, and Y is one column, and it has as many rows as I have data points in my test. So Y is a vector, A is a matrix, X is a vector. Again, we're going to use least squares to solve this and get X equals A dagger Y. And in MATLAB, remember this was X equals A backslash Y. We did all of this for a guess at gamma. And so we could guess a different value of gamma and get a different set of parameters in our X vector. And we could repeat this. We would need a way of telling how well these parameter values actually estimated the voltage, and so I would simulate, once I found X, I would simulate this equation here and find the error, and I would maybe add up the squares of the error as a metric, and I want to minimize the root mean squared errors between what the model predicts and what I actually measured. And so that's RMS, root mean squared. It's square root of 1 over n sum over all of the i's of v minus v estimate squared. That is a good metric to use in order to do our optimization. Lots of ways of making that optimization work, but you could simply just scan gamma over a range of values and look for a minimum, and the function is fairly smooth, I've seen. So you might get something like this. So this is gamma, and this is RMS error, and you'd say, oh, well, this is the value of gamma to use. It gives the least RMS error somewhere in there. And I would also use the X parameters, M, M0, R0, and Rj, corresponding to that gamma. And that is the best model that I have that matches the lab test data that I collected. That's the basic idea. To implement this in MATLAB the first time requires a fair amount of work. And so I've taken some steps to help you with that and built a toolbox of MATLAB codes that you can use to automate this a little bit. And I'll describe that in the next sections.